So, hello, welcome to the next talk. I will present you a new Eclipse project, APP4MC, that will provide an open source development platform for embedded multi and many core systems. So we are a project now for 2 months and are brand new in that environment, but we have a longer history. My name is Harald Mackamul. I'm working at Bosch in the central research, and I participated in publicly funded projects that were dealing with this topic and are now the project lead of the APP4MC project. So what will you hear in the next 30 minutes? I will explain what is the relationship between AMALTHEA, APP4MC, and all the different names related to this. I will give a little bit of a motivation. So what is the challenge in embedded multicore related to conventional multicore systems on a desktop, for example? I will describe the platform more on an abstract level, so I will not go into detail and describe how we did our data models and how we did the content of our models, but more the techniques around that. And I will show you a short demo, some slides that are related to our current release. And at the end, I will show an outlook. What are the next actions in the APP4MC project? So at the beginning, we started a publicly funded project already in 2011. So it was a European funded project, and we started to develop the data models that are now the basis also of this project. We had a clear contract with all the partners to publish our results as open source. So all our releases from the beginning are published under the Eclipse public license. And after 3 years' work, we released the first official release 1.03. And this was the one that was also published and was downloadable on our website. So we continued in that release cycle. So we also released in the new project now 2 releases, 1.1 and a maintenance release now in October. And the goal now is, the goal of the second project, AMALTHEA4public, to establish a community to make it as stable as possible that this topic can continue even after the end of the publicly funded European projects. As a number, we are now around 20 partners from 4 countries in this AMALTHEA4public project, from Sweden, Spain, Turkey, and Germany. So I will present mainly the data models that are related to the description of multicore systems. There are other activities from other partners that I will not concentrate on because they will not be part of the Eclipse project. Okay, we try to have a next release in the first quarter next year, if all is as we plan it. You see here the website amalthea/project.org. Till we have an official download at Eclipse, this is the official download site. And you can also see how many downloads were done till now. Even the former releases, we have around 800, 900 downloads, what is not bad for this kind of software. Now, why did we start this project at all? So, what are the challenges in embedded multi-core systems? I tried to describe it in that picture. So what we have to describe is software and hardware, the software structure and the hardware structure on a good level of abstraction that matches our challenges here. So you can see the software as these blocks that are related to each other. So that can be a data flow, synchronization, but in any case, it's a sequence of execution. And the first thing we now have to do is we have to decide how can we split up this software that it can run in parallel. This is in the first step independent of the hardware, but in the second step we have to do a mapping. So where do we want to have these different parts of the software now in the hardware level? So for example, if there is one task that requires a lot of data, perhaps this core is a good choice because there's a local RAM that can be accessed much faster than the other one, only as an example. And if we look into detail of one of these boxes, we always have a representation in memory. So the instructions and also the data is located somewhere in memory, and on multi-core systems, especially if you have heterogeneous architectures, it's necessary to deal with the mapping of instructions and also data, because any conflict that occurs here will slow down the execution on the cores then. If you remember the boxes, in a typical software in our domain, we have about 1,000 of these boxes as software blocks. And in this image here, they are placed on the circle, and the connections are data communication between these different things. So this was the old style of the software. Communication was almost for free. So the main challenge was the scheduling of the computation. So in which sequence do we compute the different steps? And that was good enough as an optimization of the software. Now we have a much different situation. This is an example here where we have different cores connected via a crossbar. And for example, you see here that an access to a local RAM will cause one processor tick. A connection to another RAM are already 15. Connection to system RAM, 11 ticks. Connection to another, or communication with another core, even more expensive. So now it does really matter where to place the different programs that will be executed, but also where to place the data. So I already mentioned this amount of 1,000 software blocks, and we can say it's about 20,000 data elements. That is also typical. So it's not possible to do this by hand, so we need sophisticated tooling to deal with that optimization problem. So as a marker, cross-core communication is the bottleneck. And we now have a tendency from multi to many core. It's always difficult to distinguish. It's the number of cores, or is it the structure of the cores? In general, we see that the multi-core characteristic was a small number of cores with symmetric communication, and all the cores are more or less equal in their capabilities. If we now require additional computing power, it's necessary to come up with new structures. So kind of network on chip structures with different cores, different communication paths. So that makes it even more difficult to place a software on a right component and to decide where to communicate, where to place the data. And unfortunately, this is not a future topic. Many of the embedded devices already have structures like this. So that was the reason why we said we have to represent software, hardware, our constraints, how to do this mapping in a data model and in a platform that can be reused and exchanged. So therefore, the AMALTHEA platform, I try to describe it on a high level, so you will see the structure of the system. I will show you some use cases where we at Bosch and also our customers already used this platform. And also describe the connection to the Eclipse environment. What are we using? What connections to other projects are there? So I already mentioned we have to deal with a lot of information that is necessary to know if we want to simulate or to do an analysis of the timing behavior. So the main outcome of our project at the moment is this AMALTHEA system model. So we try to combine all these necessary parts, like the structure of a software, structure of a hardware, some constraints, that may be timing constraints, that may be mapping constraints, where to place a specific component. There are always different influences here. So sometimes there are security reasons to have a redundant computation that is required. Sometimes it's performance issues. So there are always multiple constraints or guidance to find an optimal solution to that problem. Of course, we also do represent costs, like runtime costs, and we also represent decisions we do. So most of the computation will be done based on this model, and it will be enriched in several steps. And in the end, we will do a so-called performance simulation. As an explanation, performance simulation is not a functional simulation. We will not compute what is required in the end in the embedded unit. We will have a look at the timing. How long does it take to compute it? What are the communication between the different elements, and what synchronization is required? How long does it take? As an example, I will show you a screenshot of a commercial tool we use. So this is, if you look at it, you have here core 0 and here core 1, and there are different priorities. So if this is the beginning of the computation, then it will be interrupted by another one, or at the end, another one will start. And here are some light green areas where this process is stopped, another computation happens, and you have this kind of timing behavior. So for example, this will happen every millisecond, this will happen every 2 milliseconds, and so on. And we always have some tasks that are driven by events. So for example, in a motor control. So what we want to optimize here is we want to ensure that deadlines will not be missed, can be held, and that the overall balance in the system is good enough to have enough space to be sure that it can be computed. In a little bit larger environment, you will see this data model in the center, and this is the development cycle. And I have to make sure we will not deal with software development for embedded systems in a central way. So if you use C code or ASCII, MATLAB Simulink, modeling tools in any case, you will produce these blocks. And then we will try to do an optimal mapping and distribution of these blocks. So it's an additional task. It's not related to the functional software development, only to make this clear. And I already mentioned we have several steps here. We can define parts of the software that can run in parallel. The result will be written back to the model. We will add some hardware information, and especially here, at any step we can change the behavior. We can bring in own tools, custom tools, commercial tools, whatever is available to do a good computation optimization for the different use cases. And in the end, we also defined a trace format that clearly represents the the behavior in a Multicore system, waiting times and other things that are not formally part of other formats. So we used this to do some visualization and to have some feedback where are problems in the software, what can be changed here. So how is this used? So some use cases at Bosch. So we had a lot of work to get all the information. So this can be done at the end of a project where all this is available. So you can have source code analysis, binaries, you can analyze, you can have all sources of information to get these structure of tasks, was the name, runnables as these smaller building blocks and access to data. And then it can be used to do this simulation and optimization of the placement. But it can also be done in an early phase of the development, so that it's possible to use some rough estimations, how long will some computation take and where can it be placed. We use it, as we said, at Bosch for, in this case, timing architects tools. These tools are already able to import and export the AMALTHEA format. That makes it easy for us. We also use other simulation tools. SimtaVision announced that they want to read in the AMALTHEA format. They do not produce it, they only read it at the moment. And also Xcore was used in that scenario. And we are not alone. We have to deliver our software to the customer. In our case, the big car companies. And these are real examples. So we already exchanged models on that level with BMW, Volkswagen, Daimler, Peugeot. So this is the possibility to talk about timing behavior, but it's not necessary to share the whole software, because there are always IP topics. You don't want to show all your software, but to be able to optimize it and to combine the software of different partners, it's necessary to know the timing and communication behavior. Now, from an architectural point of view, we have this data model and also a lot of tools in the Eclipse environment that we use. So, for example, some of them I will show later in more detail. So this is the data model, the platform. We also provide some tooling, so some examples how to deal with that model. For example, for partitioning of software, we have examples or reference implementations. But of course, there are also commercial solutions that might be better. And on the other hand, as I already said, Timing Architects is a partner in the AMALTHEA projects. They already implemented this one, so this connection. But we have now other goals, new partners that will also provide some interfaces from other tools. One is Mechatronic UML from Fraunhofer, and the other one is the Mbeddr project that is also an Eclipse project. And we have some custom solutions to get data of other tools like Rational, Rhapsody, or Enterprise Architect. So it's possible to use this importer to create own ones because the data structure is public, can be used by everybody. As I said, we have some connections to other projects. We use some of them as an input. We reference to others that have data models that are similar to ours. Here, they are all based on EMF and on Sphinx. And we also use, for example, Trace Compass to show our traces. And, almost. As an example now, Mbeddr is a system that can handle a kind of C code. It's always a data model behind that, and you can generate your embedded code out of this. the goal is to extend this description with timing annotations so that we can get connections between this generated code and the measurement that we use, and that we can use it in a simulation after that. We already use Franca. It's an interface definition language that is based on work in the Genevi environment. And we thought it's a good possibility to describe these interfaces in a textual manner. It's an text-based editor, but can be connected to our data model. And as I already said, this is Trace Compass. It's not our work. The people from Trace Compass implemented an importer of our BTF format. So it's already possible to show some Gantt charts like the one I showed before in the commercial tool. So it's a first step, a starting point, and we want to improve this, to add some new visualizations to this tool, and we will see how this is possible. From a technical point of view, we use the Automotive distribution as a basis for our tools. So Bosch is active in the Automotive user group, and we define this together with partners. And so we have good chances that we use the same plugins and the same versions of the plugins. Xcore is used to define the models. We have several submodels that combine to this larger AMALTHEA system model. And also we use Sphinx for workspace handling. We use the editor, the tree editor that can be customized, and also the Sphinx validation that is now new in 0.9 in the newest version. And we have very good experiences with Extend as a language to transform data models and also to generate code. So these are the main techniques we use at the moment. We also extended the interfaces a little bit. So there is an OSLC connector with some difficulties to use this OSLC Leo project because there were no bundles defined and all the libraries have to be added manually. It's always a little bit complicated if you have to ensure that the licenses, documentation, source code, and so on is available. So it would be nice if this is included in the Orbit libraries, but perhaps this will happen. We use the Xcore tools, the new ones based on Sirius for the class diagrams and documentation. And to be honest, the connection between Xcore and the editor is not the best at the moment. So you always have to generate or to transform this to Xcore models, and you have to fix the links between the different Xcore models after that. Then it's possible. Before that, it was a little bit complicated. And we started with Sirius in general to do some graphical editors. Now, a data model is not the best to show in a demonstration, so I decided to do some screenshots. I think that's enough. And then I will show you where in the Eclipse help and documentation you can find additional information. So in general, it's not very spectacular. We have this AMALTHEA data model with different submodels, and we have the possibility to model a structure, for example, of a hardware, and we have several folders in the model of the software here. So this kind of customization like virtual folders and so is done on Sphinx level. It's easier than on EMF level directly, but it's still a little bit complicated. And as I said, I will now go through the help system. So if you download the system, you will get the included Eclipse help. And there is also an AMALTHEA documentation here with some main parts. There is a user guide. There is a description of the data models and a developer's guide here. And in the first part of the user's guide, you will see how you can create example projects with already existing data, so you do not have to start from scratch. You can use some examples to see how the model is used and how it can be described. There are also some tutorials here based on these examples, so it's always possible to perform different steps on a created model. So for example, you see here this example demo car mapping model was created as an example, and now it's possible to perform some steps on this model. So this will be a transformation of the model, and a new model will be created. This is all done by workflows, MVE2 workflows, also Eclipse projects. The main part of the documentation is the software model. So we try to describe all the different parts of the model. We try to provide some explanations, some class diagrams, some examples how to use it. So it's too much detail for this talk, but if you are interested, it's a good source of information, and to be honest, the only one at the moment. And for the developers documentation, you will see which features did we implement, what plugins are there, and also how to extend this workflow by own components. In our latest target, we also included a scripting possibility, so ease is included. So one other possibility next to our workflows will be to add some scripts that do the manipulation. Now, if you want to use the data model with other tools or other platforms, if you do not use EMF or Java, it's always good to know the schema definition of our XML files that we store, so it's possible to read them. They are included in the help here, and of course in the source code also. And another interface we implemented is the OSLC interface. So it's possible to set up a server that provides an OSLC access to the data model, but this is in a very early stage, so only some main parts of the model can be accessed in that area, but we want to extend this in the future. Okay, so this was a short overview what we now provided in our system. What are the next steps in the Eclipse project? So we are an official Eclipse project now since September. So the website is online. We have to improve it, of course. We will do it in the next weeks. And what we now have to do is some formal stuff. All the partners have to do the committer agreements. We have to do the IP clearance. And I hope that will be done till first quarter of next year. I'm not sure how long it will take. So that's it. The main part for this year in our project was to start the official project at Eclipse. We now try to extend the community, to give some examples. Some new users will also help. And so in the end, our goal is to establish this community that it will go on even after these publicly funded projects that at the moment support it. So at the end, please don't forget to evaluate. Thank you for your attention. If you have questions.